So Andy, can you please explain why you were concerned about this 20% Cold War 16 and why you wanted something better, and then the difficulties in getting that something better?
Well, one of the problems I saw, we were getting in the radiation program failures of the fuel elements. And the failure in a reactor is not an easy thing to correct. You have to get the fuel assembly out and the fuel cracked fuel element. Anyway, I spent those 18 years at Johnson Stainless Steel, mostly in the stainless steel area, and I got a good complete picture of the stainless steel manufacturing, all the different grades and so forth. And we were being pushed to generate very high temperature mechanical properties for the FF fuel element. And I thought we were walking into trouble. So one day I decided to call our director's secretary, ask him if I could come visit and talk to him. And I wasn't taking my boss along or anybody else. And he's an easy guy to talk to, even though he's against what you may be promoting. But he doesn't tell you that. But after a while, you get to the point, he's locked in to what he's decided, and he isn't going to change. And I told him, look, Milt, we're going to too high of a temperature as far as I'm concerned. Even though it's a higher efficiency reactor, but if you have a reactor that's shut down, you're not getting any power. And I said, when you stop and think about the fuel element in the reactor, the temperature going up and down, you're putting carbides, nitrides into solution, and when you cool down a certain amount, they precipitate out. And you have this going on constantly, and also the design showed that the temperature from the top to the center to the bottom was not anywhere near uniform. High in the center and tapering off to the higher temperature. And he listened and spoke nicely, and we ended up, obviously no direction for me. He just continued doing what he had proposed. So I gave a lot of thought about that, and I was earlier involved in the pressure vessel problem. So I talked to, I had the reactor materials program out at Hanford. And I said, look, Bob, I'm just talking to you, just you and I. Our conversation doesn't go beyond that. I don't want you talking to any of yours. And I'm I'm not talking to anybody at the headquarters. I said, I asked him, you're putting so many metal specimens into a assembly for radiations. I would like for you to put a couple of ferritic type of steels samples. This is before the FFTF, and to see what happens in a fast reactor. The water reactor radiation is totally different.
The FFTF didn't start up till 1980, so we're still in the 60s when this is occurring, these considerations.
Right. And so I finally convinced him, and he got the samples in. When that particular assembly got out, he got the samples, did some hardness tests and whatever they could do as a preliminary. And they looked very, very good. I said, I told him, don't tell anybody, keep this between you and I.
Can you tell him what samples were included in what you had put in? What were these samples?
These were what people, there was our radiation guy out at Hanford, and I used a water reactor pressure vessel for the first. This is early, and after I had to look, so I got into put what I call type 410s standard steel, 12 chrome, which they modified slightly and call HT9.
So that's called the ferritic martensitic
Yes.
material, differing from 20% cold work,
Oh,
which
completely.
Which is straight austenitic.
It's 12 chrome is a ferritic martensitic,
Right.
period. It's no austenite.
No, but the 20% cold work 316.
It's austenitic.
That's an austenite. So
And the only
this was a major difference.
cold work you can do to that is by cold reduction in drawing or rolling or something. And one reason I was suggesting 12 chrome, that's one of the lower chrome steels that they produce in stainless steel. And I figured with the stainless, austenitic stainless, there was quite a difference, a significant difference in what we call coefficient of expansion. And the other point is also in the coefficient of
Thermal conductivity.
thermal conductivity. Two things that were completely different from the austenitics. And somewhere in the 60s, I mentioned I grew up in the eastern Ohio, crossed the river from Wheeling, West Virginia, to small town Barton, Ohio. And they had recently built the largest fossil plant in Toronto or Tiltonville on the Ohio River. And I thought, while I'm at home, I'll call, see if I could come to visit and get a tour of the plant and talk to the engineers. And they welcomed me. I told them I worked for the Atomic Energy Commission on nuclear power, but I was coming not for the government, for me personally. And I talked to the top executives, and then they turned me over to the plant engineer. And he took me around, showed me the various parts, the fossil burning and the piping and so forth. And we came to the steam generator, and it was austenitic type stainless steel. And if you're familiar with a steam generator, they have a huge, what do you call the edge block that they weld the tubes in?
A plate.
Anyway, it's a very heavy section.
It's the end plate.
It doesn't move. And so this steam generator was about 125 feet long. And I said, what kind of problems do you encounter? Do you get any warpage, growth or something? He said, oh yeah. He said they get twisted. And since the end plates,
Tube sheet, I think it's
the
called.
tube
The
sheet
tube sheet.
doesn't move because of its very heavy and anchored. So these pipes are wanting to expand, and they are unable to, so they start twisting. And I said, how much would they expand in this 125-foot length? He said, 12 inches. If you have something that's locked in and it wants to expand 12 inches, that's a great deal of pressure put on those tubes. And at this plant, when I was working in the coal mines for a couple of summers, the coal was shipped just the way it came out of the mine in lumps. And I don't know how the utility uses it, but they finally were using a crusher, a big steel wheel about 12 inches thick, and it rotated around as they set this coal, and it pulverized it to a powder, which was put in a train that was forced into the burners. Mm-hmm. And I said, what trouble do you have with this crusher? And he was talking about having breakdowns and having to replace parts. I said, doesn't the manufacturer have some better steel? He said, they do, but the executive vice operating officer for the utility, this is a high up, he didn't want them to get the better grade crusher because that meant spending capital money on the budget. So they had to struggle with all the constant maintenance problem.
So these both fed into your concern about the austenitic cladding in the FFTS with the 20% cold worked.
Right.
This experience.
And I was thinking, if this has happened in tubes that were relatively thick-walled and commercial pipe made, some of this must be going on in our reactor fuel elements. So that's where I got onto this 12 chrome, and so between this Bob and I, we kept getting more samples and got enough data, and we then got fabricated tubing for it to make up fuel elements. While it was a small case, and somewhere along the line, our director Shaw was eased out. They were getting cool on the fast reactor because the budgets kept going higher and higher.
We're now in the 70s time period. We're now in the 70s time period where you might just remember there was an Index explosion in 1974. We became ERDA from the Atomic Energy Commission around that same time period. And so that changed the whole attitude of a dedicated atomic energy agency to now a big energy department. And so the priority of the fast reactor changed. Plus there was a president who was not for it. This was just pre-Carter. Who was the president before Carter?
It was Carter came in,
but
did a lot of the dirty work.
Gerald Ford was the president before Carter. In his last day of his administration, I think he recommended we not reprocess, which was a key element of this fast reactor program. So things became very difficult in the 70s. And that's exactly where he is now, trying to move ahead.
Yeah, I also I'd like to mention about the fast reactor. The activists kept using, that's a reactor that produces plutonium. What they didn't tell the public, that the reactor also produced various other elements that also became radioactive, fissile type of materials. And this type of reactor was being talked about, the physicists, while I was still at the University of Chicago, that the next step was to build a reactor to recycle the fuel from the water reactors. That was the main purpose, not to bury it in the mountain. And the old-timers who were there at the time, our intention was to get all the fissile material, come up with a fuel element to go into the reactor that where they produced not only plutonium, but a number of other things that you couldn't use to produce a atomic bomb.
But we have to keep in mind that the real purpose of the fast reactor was to breed, so that you could make.
Well, that was
many, because we knew that the enrichment system could not sustain a country that had like 1,000 reactors, and so it was the breeding aspect. The waste management aspect came up, but I think it was the breeding aspect that drove.
Well, both.
Let's get back to how you got your material to be considered for the FFTF. You know, you had a director
anyway.
you didn't want it. He was eased out, so that helped. And then you must have gotten it into irradiation.
Yeah, we also got some equipment in to do the end joining rather than welding. Thanks to a commissioner we had who came back from Russia, they were talking about this company that was making this equipment as if they were General Electric Corporation. And he said, I was called in and asked if I knew anything about it. Obviously, I didn't have any idea at the time. I said, he explained to me what the equipment was about. I said, I'll dig into it and find out who this manufacturer is and what is the equipment and all that, which I did. Then reported it to him. And eventually, we thought that was a better idea than welding the end caps.
Right, but now you had to get it into the design. Now you had to get it
Well,
into
we
the
did.
program, right? Because you didn't want to go directly to headquarters to get it approved, so you had to make another deal. You had to make another
Well,
deal.
we we got the thing along to the point where I talked to Ursula Evans at Hanford, and at that period, Westinghouse got the contract to run Hanford. So I would review these National Lab materials contract where I would be there for a week and it would review all the materials programs for 4 days. And I would invite all the best metallurgists at Los Alamos and all these places, some universities, and to sit in and give me their opinions. And so when I got it along, we were fabricating the fuel pins and building the fuel pins fabricated at Hanford. And Cartech was the manufacturer.
That's important. You got a manufacturer called Cartech to make the tubes for you, the cladding tubes. That's very significant.
To show you how the spy networks work, while this is going on in development, the French found out about the United States has got some really good material for the fast reactor.
Mm-hmm.
And they were coming around Cartech trying to buy some of it. And the general manager and I were close friends by that time. And he called me up and he said, should I sell it to him? I told him, absolutely not. Don't you ever sell it to him. And so we got it going. Finally, we got at the stage. I could not see myself at headquarters getting it into a budget as an item. Because all these people were locked in to what was decided on Type 316 and that. And so when I was out reviewing the program, I called Ursula's office and I said, Ursula, sometimes towards the later in the week, I would like to have a talk with you, one-on-one, nobody else. And I like it that way so that nobody can leak out anything. And if he wasn't telling the truth, I could call him a liar.
Ursula Evans was the director of the fuel program there, or?
He was the head of the materials program for the whole reactor.
Right.
And he was the vice president. And when I went to him, he had his sidekick, Earl O'Rourke.
Bill O'Rourke.
Bill O'Rourke, who was his really technical guy on the close work. And so I told him about the review I had with him. I said, if you are like most upper executives, uh, you listen to your people on an area probably about 15 minutes, never really sit to get a complete review, a good picture of the project. And I said, if I try to bring this on board from headquarters, I'll get my head chopped off and get fired. And I said, why don't you take credit for everything that's been accomplished with your group and provide enough of data and then come to headquarters and say, this is what I had the people doing, and this is something we should be doing for the future before the program is canceled out on the FFTF. And I told him, I said, from the way Congress is acting and with Carter in there, I didn't think the FFTF project was going to last very long. And he accepted it. He did his side of the job perfect.
Came to headquarters, sold it.
No, he did it. He worked it. He handled it as if they developed it and all that. And Shaw was gone at the time. Then Nemzik, I think, came out from where Hanford or Ohio. Was he from
He was from something out west. I'm not sure.
Idaho then. Anyway, when he became the director, that was for a couple of years after I talked to Ursel. Mm-hmm. He came in and he spilled the beans to him. He said, you know this stuff that is so good in our program now? He said, we didn't develop it out at Hanford. He said, Andy Van Ecke was responsible for all of it. I mean, he was speaking to them, telling them where it originated and all that. I was surprised that he did it. And so it didn't hurt me because they came around and said that was a good thing you did. But some of the immediate bosses, I didn't even tell Jules Simmons or my immediate boss because if they start talking about it,
it's all over.
That's all over. Yeah. So that's how we got it off the ground.
Yeah, and now just to put it into time context, the FFTF started up at 1980. I think by 82 it went to full power. And it ran for about 11 years, till 92, I believe.
92, you said.
It was terminated in 92. The bottom line of this work is that it appears that we have a very high performance material. And the story you've just heard is Andy contributing it. And I also hope you see how when you look back on all the things you've said, how everything led up to him getting this success.
You know, I dreamed that project, that would happen with this material. But I never dreamed that it would be so successful, never. I thought there would be some little thing, something that wasn't totally perfect.